Unknown to most people, algebra wasn't written the way we do nowadays. As a matter of fact, it wasn't until the 16th century when algebra took the form we all know. How do you even solve algebra without algebra language, you may ask?
Take an equation like x squared plus 26 equals 27. Now, you can imagine it as having a square of both sides x and a rectangle, one side 26 and the other side x. Put these two areas together and we have 27. Now, what do we do next? We can take this 26 by x and cut it in half. Now we have two rectangles of each side x and the other 13. What we can do now is that we grab our x squared and then we locate our two new rectangles this way. We are only missing the section over here, but I know the dimension of it. It is 13. So I can complete my new square and then we have 13 by 13. Now, because I added 13 by 13, which equals 169, that means I have to add 169 to both sides of the equation in order to keep balance. Which means that the new answer for the equation is going to be 196. And what's the square root of 196? Well, it is 14. So that means that each side of this square is going to be side 14. But I know the dimension of a part of the square. The square is going to be 13 plus x, which means x will equal 1. This solution, however, is not complete since it doesn't take into account that the solution can be a negative number. In this case, it could also be negative 25.
Not only algebra, but even arithmetics can be solved in a similar way. Say for example, you want to multiply 37 by 48. All you have to do is to create a rectangle and divide it in 4 sections. The divisions on top are 30 and 7, and the sides 40 and 8. You see where I'm going? Now, all I have to do is to do these simple multiplications and then sum them up. So we have 1200, 240, 280, and 56. Sum all this up and you have 1776, the solution to this problem. If you thought algebra was tough before, imagine doing it before Muhammad ibn al-Khwarizmi discovered the more simple way we know today, although probably you wouldn't have to. You see, back then in Europe, being a mathematician was almost like being a wizard. It was one of the most respected professions and one only the best could call their job. In Italy, around the 16th century, math duels began gaining popularity. Both you and your opponent will give the other a certain amount of mathematical problems, and whoever is able to answer the most questions is the winner. These duels weren't private either, as the loser will suffer public humiliation, so not only your career was at stake, but also your honor. Perhaps one of the most important duels in history was the one between Niccolo Tartaglia and Antonio Fior. Niccolo was a prodigy fit for his reputation. When he was a kid, a French soldier cut his face, causing him to stutter, hence why he was called Tartaglia, which is a nickname for a stammerer. He is mainly self-taught, as he was too poor to pay a teacher.
His biographer, Arnoldo Mazzotti, even wrote that when Tartaglia was 14, he asked a professor to teach him how to write the alphabet. But
He ran out of money by the time he reached the letter K and never returned to a tutor. On the other hand, Antonio Fior wasn't on that level. He was the assistant and student of Scipione del Ferro, a great mathematician who revealed to Antonio how to solve the Depresi cube on his deathbed. A problem no mathematician in history was able to accurately solve. Del Ferro apparently was able to solve it years ago, but kept it as a secret to secure his job, As if anyone were to challenge him, he could retaliate with depressive cubic problems. Antonio saw this as an opportunity and challenged Tartaglia.
But to his surprise, Tartaglia was able to solve all 30 depressive cubic questions Antonio gave to him. And unfortunately, he wasn't able to solve a single one Niccolo gave. But how did he do it? Well, before he was challenged, Niccolo did hear about
So that a young Antonio Fior was able to solve the depressive cube. But he stated that he didn't think he was able of such a deed on his own, which meant he was either bluffing or someone else taught him, which was more plausible.
But with the knowledge that a solution exists, Tartaglia sets to find a way to solve the depressive cube, and he does it in only 2 hours and a half. He used a similar approach on how we solve the quadratic formula.
Imagine the formula x cubed plus 9x equal 26. The cube is, well, a cube of all sides x plus a volume of area 9x. Imagine if you extend the sides of the cube, let's say a distance y, creating a new larger cube of sides z, making z equal x plus y. Now we can divide this new volume into 7 smaller shapes, 3 with dimension x by y, and another 3 narrower with dimensions x by y, plus a small cube of sides y. Tartaglia rearranged the bigger prims into a rectangular block of size 3y by x plus y, which is z. So the volume of this shape is 3 times y by z by x. But Tartaglia saw that the volume can perfectly represent the 9x in our cubic equation if the base of the rectangular cube was equal to 9. So he says 3yz equals 9. But we still have the smaller cube missing, so we add y cubed to both sides of the equation to maintain balance. But remember that x plus y equals z, meaning that the equation can also be read as z cubed equals 26 plus y cubed. Now we can use the equation on our right to see that z equals 3 over y. Substitute this result in our first equation, and we get y to the 6 plus 26y cubed equals 27. At first, it might look that we are far worse than when we started. However, if we think of y cubed as a variable, we get a quadratic formula, the same quadratic formula we solved earlier. So if y equals 1, z should equals 3, and since x plus y equals z, that means x equals 2. This transformed Tartaglia into the second person in history to solve the cubic equation.
However, the secret on how to solve it was once he planned to take to his grave. It was not only until Girolamo Cardano
persuaded Tartaglia to reveal the method to solve it, on the condition that he will never reveal it, and if he were to write a book about it, he will give Tartaglia enough time to polish it first. But as any information goes, once you reveal it to one person, might as well reveal it to the whole world. Cardano revealed the method to his assistant, Ludovico Ferrari, and it was them who found a way to reduce any quartic equation into a cubic, making them the only people in the world capable of doing so.
Cardano wasn't like other mathematicians that didn't want to publish methods or results. As a matter of fact, when he and Ferrari found a way to solve the quartic equation, he wanted to publish it immediately. There was one slight problem though. They were able to reach to the results thanks to the knowledge that Tartaglia gave to him. So publishing the results of how to solve the quartic equation will also mean breaking the oath he gave to Niccolo.
However, in 1543, Cardano got to know that Tartaglia wasn't the first man to solve the cubic equation. It was Del Ferros. In his mind, this freed him from any obligation to Tartaglia, which is the biggest technicality I ever heard. But regardless, 2 years later, Cardano published Ars Magna, containing his and his assistant work in cubic and quartic equation. He did give credit to Tartaglia in his books, however, he still didn't take it lightly. He accused Tartaglia of theft and breaking his vow. Ferrari couldn't stay quiet. For months, him and Tartaglia began publishing pamphlets attacking each other, until they decided to end it with a public debate in Milan, hometown of Ferrari. Not much detail can be found on this debate, only thing we know that it went terrible for Tartaglia. A lot thanks to the fact that the crowd was only in favor of local town boy Ferrari. Ferrari began drowning in job offers while Tartaglia's reputation plummeted and ended up dying the same way he was born, penniless and mostly unknown.
I guess you can say that the moral of the story is that sometimes it's worth making your knowledge public, and keeping it to yourself isn't always the best idea. Up to this day, the way to solve the qubit equation is still called the Cardano's method.